Kind introductions. As I said, my name is Michael, fifth year PhD student at MIT. Today I'll be talking about the importance of studying the limitations of human motor performance. So just to give a brief dive into about me and a small aspect that motivates my research. So growing up, I always played sports, namely basketball and football. In college, I played football, and now in graduate school, I play rugby. And with those contact sports come a lot of injuries, a few shown in the photos here. So I've had a little bit of experience with rehabilitation, and some aspects of it are very disheartening. So one thing that I'm interested in is trying to make that process easier for folks who may suffer from motor impairment. So going into the research, in our lab, we study how humans manage physical interaction. And we call this interesting thing the paradox of human performance. So if you see the video on the left, you see humans doing these complex interaction physical tasks as part of their everyday jobs, their everyday lives. And the video on the right, you see some of the most advanced robots of the Dr. Robotics Challenge failing to do tasks that we find trivial, such as trying to get out of the car, or walk in sand, or traverse a door. So we call this the paradox of human performance because when you look at the wetware and hardware of robots, humans seem to have inferior. So their actuators are about 2 orders of magnitude slower, their communication delay is about 6 orders of magnitude slower, and their feedback delay is about 2 orders of magnitude greater. So it appears that humans are doing a lot more with less. So the question becomes, let's keep it going. The question becomes how? And that's something that we're kind of interested in our lab.
So unmute on Zoom.
If you're on Zoom, you gotta mute.
So how do we answer this question? How do we study the complex system that is humans? So essentially what we try and do is we look at behavioral experimental data, largely a lot of kinematic information, and we split between this paradigm of trying to create simple models that describe the human, what they're doing, and then also using control theory to try and figure out what control inputs may they be using given this simple model to achieve the experimental observed data that we've collected. And in my research, I've done that in three ways that I'll go through today. And specifically, in the first, I've looked at upper limb human force control, and I've asked and answered this question that has been seen often in robotics is, can humans manage force control during motion? Today, I will convince you that that's not necessarily possible due to mechanical impedance. And then secondly, I'll show, given the understanding of mechanical impedance in humans' motor action controller, the question becomes, is this something they can perceive as well? And today I'll show you that, yes, they can. And in fact, we have penciled in some ways in how they were able to do this, specifically via path information. And then lastly, I've studied hand manipulation. And one thing that simplifies hand manipulation is this idea of coordinated movement known as synergies. And I'll also show you that this information can be used to simplify hand manipulation tasks. However, there's special nuances that need to be considered. So going into the first topic of upper limb force control. So there's these competing control theories, and the first of which stems from robotics, which is hybrid position force control, which assumes that you can control both motion and force simultaneously, so long as they act in orthogonal directions. So this leads to what we would call direct force control, which in your controller, you have a planned force that directly leads to your applied force. And the working hypothesis is if you're moving and you're applying a contact force, your areas of contact force should be independent of motion because your applied force is independent of motion. Now, if this hypothesis is incorrect, we propose this indirect force control method, which now has this highlighted impedance term where your input motion and your actual motion are connected to your applied force via the interactive dynamics known as mechanical impedance. So one thing to consider when you're testing these two competing theories is that this indirect force control method this indirect force control method will simplify into direct force control if one or of two things happen. One, your interactive dynamics or your impedance is 0, which has been found not to be the case in muscle dynamics. And then 2, your actual motion and your input motion are exactly the same. So in an experimental paradigm, if one of those two things happen, we wouldn't necessarily be able to tease out between these two control theories.
Input motion, the motion being commanded by your nervous system?
Yeah.
Okay.
So in this controller, I don't specify where the command necessarily comes from, but yeah, somewhere in the nervous system. That output space might be somewhere, and the input motion would be what leads down to your kinematics, your desired kinematics.
Why no feedback? Why is there no feedback?
This is the open loop controller formulation. So if we go back to just the working simple control model here, this control theory, we're testing this control, this open loop feed forward control right there. So there will be feedback at some point, but we're trying to test specifically is direct force control or indirect force control used here.
It's a conceptual question about this.
Mm-hmm.
So in this plan part, are you thinking like, I'm in the brain, like this is where I want to move my hand, or and to reach there, I need to like exert this X amount of force? Or you, because I can think of like two modalities of achieving that, right? I can move there with a certain force, or I can just move there.
Mm-hmm.
And like, how you conceptualize that with like that second formulation specifically?
So the input motion is exactly where you're aiming to move. So if let's say we're reaching in free space, so there's no applied force.
Yeah.
The input motion is where you're aiming to move, and then there's some interactive dynamics that may lead to a mismatch. So I think the best way to kind of internalize this is if I always forget to bring a spring somewhere, but if I had, let's say I have my input motion leading, and then I have a spring connection or a spring damper connection, whatever your interactive dynamics are, that's following, and that's your actual input motion. So differences may lead to differences in the actual motion, the input motion. The interactive dynamics will lead to differences in the actual motion. Does that sort of answer your question?
I guess I was thinking more about, you're also like explaining there like the dynamics of the motion itself, but I was actually thinking of like, if I want to reach something, I don't have the dynamics in mind necessarily of my whole path of trajectory, I just have like the endpoint.
So there's two working theories, right? It's what you're describing is, are we planning a feed forward path or just a feed forward endpoint? I can't necessarily say one is right or wrong compared to the other. I think there's been more evidence to show that it's a feed forward path. But yeah, those are two ways to see achieve that first, let's say, that problem. But with these two competing control theories in mind, what we aim to do is try and create an experimental paradigm that can tell us if one of these is being used. So how do we experimentally test these two opposing controllers? So what we did was we had our human subjects sit in front of a robotic manipulator, and the robot's manipulator moved about an elliptical trajectory all on its own, and we instructed humans to apply a constant force on this robot manipulator. And importantly, we had two sets of experiments: 5 Newton experiment where they were asked to apply 5 Newtons tangential force, and a 0 Newton experiment where we were asked to apply 0 Newtons of tangential force. The main experiment was a 5 Newton experiment where we had them alternate between 5 different blocks that each consisted of 15 trials, and each trial consisted of 4 cycles about the ellipse. So by the end of the experiment, they had gone about this exact same ellipse 300 times. And the blocks alternated between having visual feedback and not having visual feedback and so forth, where the visual feedback looked like so, where subjects sat in front of this big projection screen, which had a static white bar, which was the target force, and a moving red bar, which was their actual force. So the name of the game was essentially apply the right force so that the red bar stays on top of the white bar. And then highlighting the 0 Newton experiment. So this is a previous study ran by a colleague, Pauline Maurice, who was interested in trying to understand what velocity profile should this robotic manipulator follow to enable the best interaction. So what enables their subjects to reduce their error the best. And one thing that they found was that this velocity profile that enabled this was one that followed this 1/3 power law, which has been seen in a lot of free upper limb reaching. And essentially this 1/3 power law is a mathematical relationship between the tangential velocity and the radius of curvature. And it states that it's a mathematical way to say that you move faster along straight edges and slower around curves. So in our experiment,
Is the tangential force in the direction of motion or the opposite direction?
tangential force is in the direction of motion.
It is, okay.
Yeah, and this velocity is specifically the tangential velocity.
So did you say it was after 300 revolutions?
Yeah, so by the time they ended this experiment, they had done this 300 times.
Okay, so but it wasn't before they started doing the experiment. Like, I guess I'm asking, was there a training effect or like were you
Yeah, that is a great
getting
question.
fast learning? Yeah.
That is a great question, which brings us to the next slide. So what does subjects do? Essentially, so what's being shown here is the subject's root mean square force error as a function of trial, separated by blocks, so that at this endpoint is their 300th trial. And I guess what's not shown here is this familiarization block where we ask them to just apply a constant 5-Newton force, which we don't show the error because you can imagine if I ask you to apply 5 Newton's force on the table in front of you, you'd be like, what is 5 Newtons? But interestingly, when we look at this first block and we fit a linear model to it, we see a significant slope. And at about 9 trials, subjects' error plateaus. And then from trials 9 to 300, there's no further reduction in force error. So the question becomes, okay, despite what we call extensive practice, obviously it's probably not the limits. People could have sat here and done this for, many hours if we paid them or something along those lines. But in this experimental paradigm, why are they not improving between trials 9 and 300? And the reason is force error is motion dependent. So when we look at this plot here, shown for a representative subject, we see force as a function of robot angular position, and we see these peaks in this force, specifically at 180 and 360 degrees. And one thing that's interesting about this is when we use autocorrelation analysis to figure out where these peaks.
Was? Als du den Max Clark zur Schule gebracht hast.
When we use autocorrelation.
I don't think it was a question.
Okay. When we use autocorrelation analysis to figure out where these peaks occur, we see that they very consistently occur at this 180 and 360 degree position. And one thing to highlight is this is robust across both the 5 Newton and the 0 Newton experiment. And then also, this is robust even in the familiarization block where we're asking subjects to apply constant force and have no idea what this 5 Newtons is. So what this says is that in this task, a model that can describe this task competently, one has to couple motion and force via this mechanical impedance. Then also there's coupling from the motion that is derived from these dynamic oscillatory primitives, which I'll go into a little bit later.
Could you say where in the ellipse the 360 and 180 are they at
The outputs of the ellipse right here.
And is there something about where I'm trying to get a sense of how big the circle is.
30 centimeters by 15 centimeters. So 30 centimeters in the major.
30 centimeters more like that.
Okay, so they're going like that.
Or 30 and 10 is what it says.
Oh, and 10. So it's this is like it's more like a left to right.
Are you trying
yeah.
to ask if whether or not it's because it's on the sides or because it has higher eccentricity on those ends?
Or you're at like zero velocity this way, and you're switching from. I guess you're going down to zero. Or is it something about the limb dynamics where it's super sensitive?
Sure, yeah.
Some singularity or something.
I'm fairly confident it's not the limb dynamics because so we had subjects that started off in this initial position, so they weren't constrained to just planar motion, right? If they're constrained to just planar motion, then they'd only be able to have actuation between this joint and this joint. Now you have a 2 degree of freedom system, 2 control inputs. You don't have redundancy. Now, when we allow them to move this joint around here, there's a null space, there's redundancy, and there's a lot of different actuations you can use to reduce this error. Does that make sense?
Yeah. Yep.
Okay.
How did you settle on that shape? Like, how did you settle on the 15 by 30?
Just to be consistent with this previously published paper. Yeah.
I have just a quick question, like, would the same relationship hold if the ellipse was just rotated 90 degrees? So your long straightaways are forward, backward, rather than right, left?
That's a great question. I believe this paper, while this was not their main question, they did have conditions that showed the ellipse in this direction. The key thing though is that in all of their conditions, they did see this oscillatory motion. So the key thing is that we asked them to apply a constant force, which would look like a straight line, like so. Regardless of the ellipse position, we see these this periodicity.
So actually, you're really bad. You're really pretty good.
So the question, I would say, you say they're really bad at this task,
I
right?
mean, the force, they're bad at that moment of transition. They're, I mean, it's really great data.
Yeah, I'm really interested to see what happens if you have a square instead of a circle. How that passes.
I have an answer to that question in a couple of slides.
Are they just doing time?
No philosophical discussion.
So the robot provides the motion. So if they're not applying any force on the robot will still move. And the robot's controlled with very high stiffness gain. So the robot is going to follow the motion regardless. Some people, we had one subject who really struggled with the task, and in fact, when they were applying weird forces, the robot's entire base moved beyond just the manipulator. So.
Is it just the switching between the antagonist and agonist mostly? In terms of where you are in that path? Like, I guess it's shoulder. It's more shoulder than actual arm.
Again, I don't think it's necessarily the limb dynamics just because you have that null space.
Is there visual feedback helping?
So in the blocks in purple is where subjects receive visual feedback. So I think, here we see the initial visual feedback does help. So this is all the subjects. Initial visual feedback does help. However, they quickly plateau, and it's about the same for the rest of the experiment.
Did they take advantage of the null space? Like people did it differently, or did they all do it the same way? Because if the null space is there, and they all did it the same way, there could be an effect of limb dynamics.
Here you're saying that essentially they're just doing they've chosen one particular method that leads to a consistent motion in this limb dynamics.
Yeah.
I didn't look at that. I would hypothesize though that they all had similar strategies.
Yeah, I bet they did.
However, I think the main reason as to why we see this observation is that as we showed here, there's clearly a coupling between motion and force, which says in our control block, we must have this indirect force control method, which does have this coupling between motion and force. Now the question becomes, where do the oscillations come from? So when you think about this indirect force control method, we have coupling of motion and force. Theoretically, we have two inputs, right? We may have two inputs. We have a planned force and a planned motion to give an applied force. So there's infinitely many solutions, right? So why are they still not solving this problem? So a working hypothesis is, given this output, we have an elliptical output, which is an oscillatory motion. It's a superposition of two oscillatory motions. So if you have an output oscillatory motion, they have to have this oscillatory output motion, then it's likely their planned motion is oscillatory as well. Now, if our planned motion is oscillatory and is connected to our applied force via these interactive dynamics, then you can start to understand why there is oscillatory output motion.
That was too fast for me.
Okay.
Are you saying that it's necessary? So like this is the outcome that you always get if those are the restrictions of the system?
Yes.
Oh, really? Okay.
Yes.
Doesn't that mean you would see this for a circle?
Mhm.
And you do?
We did not test it with the circle. But in this particular task,
Because the errors are largest at where the eccentricities
The
are.
highest changes on the sides, yeah.
I think that's what's driving the variation.
Yeah, because you're accelerating the most.
Yeah,
at
that's
most. But in the circle, you would see a constant
curvature.
So that would be a good thing. Yeah.
So I think another way to ask that question is you're saying the reason we're seeing these high errors in force is because they're accelerating at these points, right? So in the previous study, they ran a similar study where this velocity profile was not following the 1/3 parallel, rather it was constant. So the velocity profile was consistent across this entire ellipse, and they still saw these peaks.
I forgot that the velocity was changing.
Mm-hmm. Well, I think that's what you said.
Well, I just meant the shape of the ellipse.
Yeah.
Well, even with constant velocity, you're still getting a change in your acceleration because your velocity vector is changing faster. So
Yeah,
the
right.
derivative velocity with respect to like ground is actually differing if you have an ellipse versus a circle as well, right?
So I think there's, I guess, two confounding factors. One of what you're talking about is the change in the directional velocity, which is important because they're applying this, they have to apply directional forces, and then also the change in the actual velocity profile. I have to take a second to work out the math, but I'm pretty sure in one of these conditions, right, you have these two variables. Now you can find a case where there's no change based off of the confounding of these two variables. And I'm pretty sure in the previous paper they tested that and they still found these peaks.
Cool.
And I think the important thing though is that this particular velocity profile, despite all these confounding factors, in the previous paper, the whole reason for conducting that paper was to find the optimal velocity profile. And this was the optimal velocity profile. So even if we gave them a different velocity profile that may have different acceleration vectors or may have accelerations that don't change, subjects are going to do worse. Do you guys have any other questions on this topic before I go into visual perception and stiffness? Cool. Sorry. Why is this important? Good. So I think, it's important for obviously two things, human quantification of performance and estimation of human intent, right? So we're all sitting here asking, why is this line not straight? Why is it oscillatory motion? And if we were to sit here and come up with a control task where we wanted the subjects to apply a constant force about an elliptical trajectory where they have some constant force here, and we try to use that as our control input signal, then you can imagine you see systematic errors as we see here. So the importance of this study is that we found a limitation in humans' ability to apply forces during motion, which can lead to, misunderstandings when you don't understand that during when you use it for some sort of control of maybe some sort of wearable or something along those lines.
One question. Do you think that if you were to look at, because you're the red bar and the desired one, that's only in the tangential direction, right?
Yeah.
Do you think that at the endpoints, the error might be even more off axis, I guess, like in some centripetal direction? Like I think that in the yellow part where it's long and flat, I think that they'll have less force being directed off the tangential direction. And then during the eccentric one where it's really curved, I think that they'll be anticipating it's about to go this way, right? And so the off axis force.
Yeah, it's like, are they getting the magnitude of the force right? And are they getting the direction?
Yeah, that's right.
And it might be harder as you get more eccentric.
Yeah, that's definitely certainly possible. I don't think the visual feedback has anything to do with that though, because the visual feedback is giving them visual feedback specifically on both the direction. They're getting visual feedback on the tangential force, which has direction encoded into it, direction and magnitude. Right. And then I guess this wasn't published, but I also looked at just the magnitude of the force. You can't really say there's errors because we told them to apply forces in the tangential direction, but the magnitude of force also has this oscillatory motion as well.
Michael, I gotta go. I told you 20 minutes would turn into an hour.
Wow, this is great. I enjoyed the conversation. So the next topic is the visual perception of signals. So I think previously, in the previous section, I showed that mechanical impedance is important for motor action. So the question is, if this is something that is encoded in our motor action domain or how we control our motion, is it something that can be perceived as well? One thing that motivates this is that humans are really good at extracting latent information from visual observation. So as you guys can all see, in the point light illustration shown here, you can see just dots of people moving. You can very easily tell that someone's walking, jumping, or climbing stairs. That's something you can all do in your everyday tasks. So the question is, okay, if stiffness is something that we encode in our movement, is it something that people can perceive as well? So a previous colleague of ours, Professor Huber, ran the study where subjects sat in front of a computer and observed this two-link manipulator move and asked if they could rate changes in stiffness or estimate the stiffness. And she found that yes, subjects could, however, they were unsure how. And that's where my work comes in. So the working hypothesis was that if we are using our understanding of motor action and its relationship to motor perception, then the way subjects are doing this task is inherently embedded in the controller. And specifically, one thing that we are interested in is what motion cues are subjects using to estimate this stiffness, and what aspects of what's being embedded in this controller are subjects looking at. So in the previous portion of the talk, we all were talking about this velocity profile and how that velocity profile was optimal for interaction. It's also shown to be how humans move in free reaching and upper limb tasks. So the question we're interested in is this velocity profile important? So in the previous study that Professor Huber ran, the simulation followed this vertical 1/3 power law. My question is, okay, if temporal information is important, then manipulations to this 1/3 power law velocity profile should inhibit subjects' ability to estimate stiffness. So that's what I went and tested. And specifically, I ran an experimental paradigm where subjects sat in front of a computer screen, observed this two-link manipulated move, asked them to rate the arm stiffness on a scale from 1 to 7. And I guess details of the experiment, subjects saw 6 different joint stiffness conditions, 5 different times in a block randomized order. But what's important is the control law, right? So I said the reason people are able to do this task is because there's time between the motor action domain and the motor perception domain. And the motor action domain is described in the control law that we use in our simulations. So the controller was modeled to have the arm dynamics of an adult male reaching in the vertical plane subject to gravity. And the controller is shown here. May look somewhat complex, but it's quite simple. It is the superposition of 2 attractors, 2 impedances. The first impedance is this attractor to a circular trajectory about the endpoint, and the second is this, so which is shown by these terms here, and the second is an attractor to a nominal joint configuration by your elbow, your shoulder, and your elbow, which is shown by this term here. So essentially, when we're asking subjects to rate this arm stiffness, what we're changing in our simulation are these 2 values. We're trying to see if people can tease out the difference between these 2 values for the simulation.
What is KS and KE?
KS is the stiffness of the shoulder, KE is the stiffness of the elbow.
Okay, got it.
So yeah, as I previously motivated, the open questions are what motion cues are humans using to estimate stiffness? And I guess I want to take a step back and highlight how remarkable this task is. If you take a second to think about it, stiffness is a relationship between motion and force. We ask subjects to sit in front of a computer screen, watch a two-link manipulator move, and estimate its stiffness. All they had access to was motion information. So if you think about like stiffness as Hooke's law, F equals Kx, they're finding K with just X. The question was how? What aspects of X are they using?
Like, was it qualitative? Like more stiff or less stiff than something else?
Yeah, so specifically from 1 to 7. So the simulations that they saw were, in my case, elbow stiffness changed from 0 to 50 newtons per meter, which means nothing to people who haven't interacted with the robot before, which was most of our subjects. But they rated it from 1 to 7.
So did you get them to interact with the robot so they could actually see what 1 and 7 meant beforehand?
No, not at all. Which once I get to the results will make it pretty interesting as well. But so what simulations did I show? So again, I was interested to see if temporal information was important, meaning velocity and its derivatives. And what I did was I created a new set of simulations that violated this power law relationship. So the original experiment that Professor Huber ran was consistent with this power law relationship. What I did was create new simulations that had the same path information, same trajectory or the same motion, same path information as in displacement, not motion, displacement, and then the temporal information was changed to the velocity and the derivatives. And I did that 3 different ways. So you see this original experiment is consistent with that power law relationship where we see it is faster along the straight edges and slower around the curves. And then we now have a new condition where it's constant around this velocity, around the constant velocity. And then we have an inverse condition where they're going slower around the straight edges and faster around the curves. And then we have a completely variable condition that completely violates this power law relationship.
What is R of T?
R of T is the radius of curvature.
Okay.
Yeah. It's inherently a function of time because the velocity is a function of time.
So the dimensions of K would change with beta?
This K here, this K is a constant gain. And we tune the constant gain so that the period is the same, just so that's not something people have access to change. But yeah, K is a constant gain. So what changes with beta is essentially the tangential velocity here. So what do we see? Subjects can estimate stiffness and they can do it across all 3 tasks. So when we look at the simulated joint stiffness in our simulations and the stiffness rating, we see this positive linear effect of simulated joint stiffness rating. So you asked previously, were subjects able to figure out what's the least stiff and most stiff prior to doing this experiment? No, they were not. They could still tease out these differences. And then shown, I guess here, is individual subject data. And what you can do is you can fit this, the relationship between the subjects, the simulated stiffness and the stiffness rating. You can fit a linear model to that data. You can use the coefficient of determination as a measure of how good subjects were at this task. And one thing that we found was that condition or the velocity profile had no effect on the subject's ability to estimate stiffness, which shows that subjects are looking at path information rather than temporal information in doing this task. One other.
Do you have, just by chance, have those videos here that we can get an impression of how this looks like? Like how the different stiffnesses and the different velocity profiles look like?
Sorry.
It's Shift F5 to play from the current slide. Oops. Oh, then Shift Function F5. I guess. Funny. Yeah.
That just works. So this is exactly what subjects saw in the experiment. So they pressed this green button to start the trial. They observed this 2-link manipulator move. They rated stiffness. Feel that right? They rated stiffness from 1 to 7. They repeated that 7 times. So to compare the conditions, here's a video. We won't go through all of it, but this is the elbow stiffness with 0 of the 4 different conditions. So you can kind of see in In this condition, so look like the bottom position, you'll see in the original case, it's not as easy to see it in this condition because there's not a lot of high curvature. But at the endpoints of the motion, you can start to see where some of the differences lie.
Thank you, that helps a lot to understand.
Do you think it would be fair to say that, like, the participants are still using the motion information to detect the stiffness, like the movement of the manipulator suggests certain types of accelerations, which would suggest certain types of stiffnesses, but the ability to detect the stiffness is not dependent on the velocity profile, but the acceleration information from those profiles is still important for detecting the.
Inherently, by changing the velocity information, you're changing the acceleration as well.
Yeah, I was just going back to what you said about like they only needed the path, but I think you still need to like the motion of.
So
how to phrase.
I think maybe what you're getting at is, so what I've showed here is that their ability to estimate stiffness is path dependent, but you're asking is temporal information important in some degree as well. So in fact, I guess to answer that question, does temporal information have any influence? We ran a second experiment where now we just showed subjects one arm stiffness over and over again with just different velocity profiles. And we asked them to rate the stiffness of that. So if they had done this task perfectly, they would have chosen the exact same button over and over again 20 times. And on average, that's not what subjects did. In fact, what we found was that people perceived the vertical or the velocity profile that was that followed the 1/3 power law to be less stiff than the others. But between the violations that we explored, there was no statistical difference. So there is some information encoded, temporal information, velocity profile, has some effect, but it is subordinate to the path information. I think that answers your question.
Yeah, I'm thinking a specific thing when you say path and temporal, but I think I'm aligned with what you mean by this.
Sorry, so path I mean displacement, and then temporal I mean velocity and its derivatives.
Yeah.
So to conclude, we show that people are able to directly infer changes in limb stiffness from visual observation of motion, which suggests that stiffness is something that's encoded in people's perceptual model. And then we showed that path information predominates temporal information when subjects are doing this task. So why is this important? I think one thing that's important is take back the whole hypothesis. The only reason that we think subjects are able to do this task is because they're using some information about how they're controlling their own movement, which suggests that now you can use these perceptual studies to learn a bit more about human motor action. And then from a rehabilitation standpoint, I guess one thing I forgot to highlight here was, so here is our best subject with this coefficient of determination of 0.9. That person was actually a physical therapist, which is really interesting in the sense that oftentimes when we talk about stroke patients, people talk about having abnormal muscle tone, which hasn't necessarily been quantified to our understanding at least. But some people believe it has a similarity between muscle stiffness. So going back to the impact of this, okay, if what's being encoded is what physical therapists see as a valuable measure, this muscle tone, and we can figure out how to observe it with just visual observation of motion, then we can create some systems that can measure this stiffness as a performance metric throughout rehabilitation using just cameras, which you can imagine is something that can be ubiquitous in home and also cheap. And then lastly, it's just important, the limits in the motor action domain may not necessarily apply in the motor perception domain, which kind of leads to questions of trying to understand, are these limits based off of neural constraints or biomechanical constraints, which I think is an interesting topic.
And you say that because the power law was not deterministic in this?
The power law did not inhibit subjects related to this task. Right? So I guess going into the last portion of my talk, so I've studied essentially human hand kinematics and specifically this idea of synergies, which are coordinate-related dimensionality reduction technique. And the idea is that when you have your hand has greater than 20 degrees of freedom, 20 joint degrees of freedom. However, when you use your hand, you rarely ever move each joint individually. Rather, you move many of them simultaneously in this coordinated movement called a synergy. And back in 1998, Marco Santalo discovered this and used principal component analysis to figure out this mapping between the joint degrees of freedom and this principal component space, and showed that two of these synergy-based degrees of freedom, these principal components that he calls, can account for 80% of the posture during a wide range of hand grasping. Which can say that maybe you can possibly hypothesize that these synergies might be a neural command that allows you to use fewer degrees of freedom to control this high degree of freedom space. However, most of the literature in that space looked at grasping, and I'm specifically interested in manipulation. So I make the argument that picking up a tool and using it are very different. So picking up a pencil is different from writing with it. Picking up a screwdriver is different from screwing with it. And you can imagine if the kinematics in those two tasks are different, they may lead to different synergies. So the open questions I aim to answer were, do synergies emerge during object manipulation and tool use? And if so, are they the same as those that emerge during reach and grasp of those tools? So how did I ask this question? So what I did is I ran an experiment where I had a set of tools and I asked people to reach and grasp those tools as if they were going to use it. I measured their kinematics with a data glove that you see in the video shown there. And then I ran an experiment where I had subjects manipulate those tools to achieve a functional task. So the functional task I chose was to have subjects install this wire harness onto a mock electrical cabinet. And I think one nice thing about this task is it involves physical interaction, it involves tool use, it involves interaction with a complex object. And these are all things that robots today struggle with. So yeah, you can see the fake subject there doing the task. So with the data collected, what you can do is now you can stack your data and create this data matrix of joints as a function of time. And you can run singular value decomposition on this data. And essentially from singular value decomposition, you end up with a rotation matrix times a stretch matrix times a rotation matrix, which is a fancy way of saying eigenvector decomposition. And your right eigenvectors end up being these postural synergies. So they're essentially a vector, a synergy vector of how all the joints are coordinated. And then your left eigenvectors are a temporal weighting, which show how all those coordinated movements are enacted. So you can imagine if your first synergy is something that is an open-close, it's a posture that says all these joints are coordinated like so, then you have a temporal weighting that says all these joints move like so. And then your stretch matrix in the middle is your variance matrix, how much variance is accounted for by that synergy vector.
Can you say again, what are you measuring?
Joint kinematics of the hand. Sorry, I did not say that previously. So I'm measuring, as people were doing the tasks in the video that you saw, I'm measuring the kinematics at each joint, specifically the three joints of each forefinger, including abduction here. I'm also measuring palm arch, and then wrist, pitch, and yaw, and then 4 degrees of freedom at the thumb. So this flexion, abduction, and then inward thumb rotation.
How can you interpret the left and rightness of the eigenvectors as postural and temporal things? Like you get a U sigma V, what makes you think that V has something to do with posture and U has something to do with temporal things?
I think you know about dimensions.
Yeah, it's something that falls out of the math. So yeah, it's kind of how the math works. So essentially what you're doing is, like, let's say you have a matrix and you do singular value decomposition on the matrix. Your left eigenvectors are going to tell you the main eigenvectors, the main directions in your row space, which is the temporal space. Right. And then your right eigenvectors are in your column space, which are the feature space, which in my case are the joints.
So this is for a single person?
Yeah, so I do it for individual subjects.
Yeah.
So were you measuring that with glove?
Yeah, or a cyber glove. Yeah. So I can do that. I did this in my case, the data where I compared reach and grasp of all the tasks that you saw previously, and manipulation of all the tasks, and also compared one tool to another tool, just for a direct comparison. And I've only done it on individual subjects, not all subjects pulled together. So the first question was, do synergies emerge? And one way that people answer this question is, when you look at the synergies and the variance accounted for by them, is there a reduction in the degrees of freedom space? So as I mentioned, my data collected 23 joint degrees of freedom, and in the synergy space, when we look at these variance accounted for curves, we start to see with much less than 23 degrees of freedom, we now have high variance accounted for. Now, one thing that's interesting is when you look at these three cases, the all-task, zip tie, and screwdriver, we start to see differences between the reach and grasp variance accounted for, shown in red, and the manipulation variance accounted for, shown in red. And one thing that people do throughout the literature is ask the question, okay, how many synergies do you need to accurately account for this data, or account for the information in this data? And that's an open research question, but one method that people have chosen is you want to have a cutoff for your variance accounted for. And one that I chose, that people have chosen before, is having a variance accounted for of 90%, and then an additional synergy beyond that does not add greater than 5% variance accounted for. And when we look at that metric and we compare that between reach and grasp and manipulation, we see in the all tools case, the zip tie case, the screwdriver case, manipulation requires more synergy-based degrees of freedom than your reach and grasp. That's not the case for the scissors, which I think is sort of interesting. When you go and grasp a set of scissors and you put your hand in a set of scissors, the object physically constrains your hand, which kind of talks about the confound between how much of this is a physical, a biomechanical constraint versus a neural constraint. So, takeaway from this slide, do synergies emerge? Yes. So the next question was, are reach and grasp synergies and manipulation synergies the same? So one way to compare synergies is cosine.
Can I ask you a question? So if you were to just shove off those extra components that you don't need of you think all those tasks that you showed, do we be able to do them successfully?
So that is a great question. I think that's on my future work slide. So I'll get there. But yeah, I guess the question of are reach and grasp synergies and manipulation synergies the same? Synergies are just vectors. So you can take this illustration here. Cosine similarity is a measure of cosine angle between two vectors. If the two vectors are the same, the angle between them will be 0. Cosine is 0 is 1. So cosine similarity of two vectors that are the same is 1. Two vectors that are orthogonal, cosine of 90 would be 0. So you can apply that to matrix math. And if you end up with two synergy vectors, or two matrices of synergies that are exactly the same, and you look at a confusion matrix of the cosine similarities, you see a bunch of 1s in the diagonal and 0s everywhere else, the identity matrix. So I did that in my data, and here for a representative subject, where 1 was represented by black and 0 is represented by white, you see that the synergies between reach and grasp and manipulation are not the same. So the first synergy, the lower order synergies, may be similar, but then they start to taper off. One thing to quantify this tapering off I did was to plot the cosine similarity, the diagonal value specifically of this cosine similarity as a function of synergy order for all of my subjects. So each gray dot represents a different subject. And you can fit a linear model to this data. And as you see here, the linear model all has significantly negative slopes, which show as we get to these higher order synergies, the difference between reach and grasp and manipulation is greater. So what does this say? When we look at synergies, we use it as a way to simplify our understanding of hand motion. And on the previous slide, I showed you that, or 2 previous slides ago, I showed that to simplify hand motion manipulation tasks, you need more synergies. So now on this side, I'm showing, okay, well, if we're using those synergies that we've studied throughout the literature in reach and grasp, and we're just now looking at more of them, I showed that that's not enough, because once we get to these higher order synergies in reach and grasp, they're increasingly different from manipulation.
What is the zip tie one?
What is the zip tie?
I'm asking, so they zip tie a bundle of cords, or?
Yeah, they zip tie a bundle of cords, yeah. And then the scissors, they cut the zip ties, the excess tips of the zip ties. Screwdriver, you see them screwing in.
Do you think, to his question, do you think it's obviously, yeah, a more complex task is going to need more synergies. And if you were to like actually reconstruct the motion with those synergies, you'd get a majority of the motion of the hand, but maybe the small little movements of the fingers or something like that as they're trying to manipulate the screwdriver may not be captured because it's not a gross movement. Basically, it's like
so it's all about how much variance is accounted for, and by that coordinated movement in the data. So you can imagine if you go and grasp a screwdriver, your motion's just going to look like so, right? Maybe if you're using a screwdriver, there might be less coordinated movement because you're doing this finger gating type task. So you might have some coordination there, but it's going to be a lot of more. I think of it as coordination versus individualization, if that's a word. And essentially, there's going to be less synergies if each finger or each joint is moving independently.
This question, are the dimensions normalized by the standard deviation?
Dimensions normalized.
So like all your joints, are they like, so what he's saying, right? Like you're gonna have a lot more variance doing this than you're gonna have doing this. Meaning that by default you're gonna have like dimensions that are always gonna be like more highly variant than others. So I guess are they normalized by the variance to begin with before you?
Yeah, no, I do not do that. The reason I do not do that is because what's important for these synergies is looking at the coordination between the joints. So let's take the finger case, and if we're looking at a finger motion that's like so, and we say like this joint moves 1 degree, this joint moves 2 degrees, and this joint moves 3 degrees all together, knowing that that's the relationship between them is important. Now, if we remove the variance amongst all those, then the synergy we'll get is that all these joints move 1 degree, 1 degree, 1 degree. So we lose out in that information. So it's I guess for people who haven't worked in this principal component space a lot, so affecting your data, all the pre-processing to your data is going to affect the endpoint results. I guess the best way to think about it, not the best, but a good geometrical way to think about it is you're decomposing this data into a rotation matrix, a stretch matrix, and a rotation matrix. Now, if you do a pre-processing effect that is akin to a rotation or a stretch, you're going to affect your rotation or your stretch matrices. Your variance, when you're saying you're going to change the variance beforehand, that's akin to stretching each of the column vectors in a sense, right? So then you're going to change the variance accounted for, but also you're going to start to change, you're going to start to change the variance accounted for, and maybe that might be not as susceptible to having high variance because one joint's moving greater than the other, but you're also going to lose information about how those joints, I guess, in the rotation matrix rotate together.
No, but yeah, we can pick it up.
I'm sorry, you put all the tasks together, right?
So in the all task case, in the upper left.
Okay. And then you did so. Okay.
Yeah. So I guess the takeaways here are reach and grasp synergies differ from manipulation synergies. You need more synergies to describe manipulation, and when you compare the higher order synergies from reach and grasp and manipulation, there's a larger the difference starts to increase. And I'd say future work should investigate these differences, but I think the question that you kind of alluded to previously is kind of why is this important? So the question that you kind of asked was, if I gave someone the synergistic space, are they able to achieve these tasks? I think that's a valuable research question. Why? If you think about our controller space, people have created prosthetic hands based off of this synergy space. They've given amputees a hand that now has this reduced degree of freedom space based off of these reach to grasp synergies.
Sorry, I'm just going to say, how different might it be instead of using from like kinematic synergies, we're using like muscle activation, so EMG synergies?
Yeah, so people have studied that as well, and there is a correlation between muscle synergies and kinematic synergies, as you can imagine, just based off of muscle dynamics and biomechanics. But yes, synergies do emerge. There's different techniques in extracting them that leads to the math, because muscle activation is inherently positive, which isn't consistent with singular value decomposition. I guess I'm not sure if I'm just saying words or if I'm answering your question.
No, I was just curious whether, like, if you go back to your example of the grasping and the manipulation, would you see the same kind of behavior of needing more synergies at a muscular level for the manipulation versus grasping?
Yeah, so I would hypothesize yes, because as people have shown, there's a relationship between kinematic synergies and muscle synergies. So if that relationship holds true, which I would hypothesize it should, then we'll still see the same, or we'll still see a greater variation in muscle dynamics when we're doing these manipulation tasks. But yeah, so I guess thinking about a prosthetic device, I think the question becomes, okay, well, if people have designed these prosthetic devices and we're giving people synergy-based hands that are designed for grasping, the question is, are they going to be able to do a manipulation task now? I think that's an open research question, and I think my work shows that you should study manipulation if you want to be able to do this task. And in fact, I'll skip that. One thing that I'm interested in next is actually doing that task in a virtual environment. So the beauty of a virtual environment is you can design prosthetic hands and change their actuators however which way you want. So what you can do is you can have a human do a manipulation task in a virtual environment. You can constrain their hand to have a different subset of synergies. And you can vary that between reach and grasp synergies, manipulation synergies, complete individual degrees of freedom, all sorts of combinations in between.
For like a single finger, you have one tendon that crosses all these joints, so they're necessarily coupled.
Mm-hmm. Yeah, so that's a great point. So kind of as we showed in the scissors case, these kinematic synergies especially are all sort of task dependent, all sort of biomechanics dependent, and all sort of based off the physical constraints of the object. Now the question becomes, we see them in the muscle space as well, which has less of those constraints, but it still has constraints. Now I think the very active research question is the neural presence of these synergies. Is there a neural constraint that leads to these muscle synergies that we observe? And I've recently seen some evidence suggesting that. I think one of the interesting studies was someone did some electrical stimulation of a human's brain during open brain surgery. I'm sure I'm fumbling the words, but and they found that stimulating, like doing direct electrical stimulation of an aspect of the motor cortex would activate the same synergies that you see in muscle synergies observed during some sort of grasping task or reaching task. So to say there's increasing evidence that there is a neural constraint on these synergies.
There's a lot to unpack there.
Yeah.
Like the specificity of electrical stimulation is like insufficient to be able to say that. So like if you activate a bunch of neurons that
It's not well controlled.
Yeah.
I guess I've been away from the space for a while, but so a lot of the EMG controls for prosthetic hands are, linear discriminant controllers are, you're just classifying a certain pattern of EMG to control the hand. Have there been synergy-based EMG controllers for prosthetic hands? Like kind of similar to what you're trying to do here, you're going to do it with the kinematic space,
Right.
Or position space.
Right. So your question is, has there been
Like synergy-based
EMG controllers?
Yeah, for prosthetic hands.
Yeah, there have been. And I think recently the synergy prosthetic hands have kind of moved from the classification of, a different posture. So rather than just be open, closed, to trying to do, instead of a linear discriminant analysis, more of a linear regression.
Yeah.
So how far open and closed are you, actuating that motion? There's challenges with that. There's essentially machine learning control problems with that method, as you're now asking it to do greater things. But
You're basically getting, I think what I was getting to in my mind was wondering if your controller would potentially help with that gradation of control. Maybe a little bit more.
Yeah, I think
either controlled or smooth than say an EMG.
I think it definitely could, but the big if is, can we get a signal that's useful for the open and close from an amputee? The degree of open versus close for an amputee. I think getting an on-off signal has been done for years, and it's been done for years because it's inherently easier. But
Wonder how many of your tasks had very much motion in this plane? Like, because I feel like those would be the degrees of freedom that explain the least. Because then, you reach and grab, very rarely I feel like there are motions where I would do this.
Carrying people off.
Yeah.
So to this podcast.
So it's pretty interesting. The first synergy is almost always this sort of motion, and the second synergy is closer to a pinch, but really dominated by the inward thumb rotation. And the thing that makes this interesting is people have studied this task, and I think in finger spelling, so sign language, which I imagine has a lot of these sort of motions in it, and it's still seeing that this is the first synergy. So I think there's obviously the biomechanics constraint to that aspect. I'm actually in the process of running a study on trying to study piano playing, just because I thought, what's the most complex manipulation task you can think of? And I'd say it's piano playing that I can think of, hoping for better suggestions. But in fact, that has kind of more attribution of this sort of motion and then the synergy space, interestingly.
I know nothing about pianos, that would be an Antoine thing, but I wonder if you look at different pianists and their pieces, if if they adopt some synergy across all of their songs, and so their hand has some pattern and then it just plays different. It plays similar.
Look at
it leverages same. Yeah.
Look at the sheet music, see the intervals.
Okay, now we're doing sheet music synergy.
Oh, these are big open chords. They're probably spreading a lot.
Yeah. So we just collected data from a set of pianists playing these pieces, and task complexity ranging from, I guess, what they range is very easy to very advanced. And we're actually looking at that exact question of, are these synergies specific to difficulty? Can these synergies tell you something about how difficult this task is? Because piano playing is also a nice task where there's a consistent measure of how difficult this manipulation task is. And then also kind of ask, are synergies unique to for this task, where inherently if you're playing the piano, you're asking them to do the exact same task, the exact same biomechanics, but are there synergies unique to a style of playing, or are they unique to the piece that's being played?
I guess for piano playing, there's a little bit of a confound with hand size and necessary biomechanical difference, necessary difference in synergy to hit the same chord, given a difference in hand size. Does that make sense?
Yeah, I didn't think about that.
Do they have variable size pianos?
They have kid pianos.
They are.
And keytards.
I wonder if I was struggling.
Yeah, that's a good point.
But I think 6 is right. Hand size. I was gonna say after you pointed out,
But I
like
think
hand side
that's
is probably gonna be the
something
biggest determinant.
Composers.
And the piece that you're playing too, like depending whether you roll up to the black keys or not.
But I feel you'd expect to see it because there's some notes that just will never go together, right? Or sound notes
Yeah.
together, so you'd expect to see the patterns in the music reflected in the synergy.
That's pretty cool.
That's a good idea.
Well, that was my talk. Acknowledge my colleagues and funding sources. So, yeah, it's linked to my LinkedIn if you guys want to stay connected.
Thank you.